For you to really understand the third law of thermodynamics, you have to take note of one concept. The concept is called microstates. Microstate is a specific arrangement of particles of a system. A system can be anything that you can see with your naked eyes under study, right? So a microstate is the specific arrangement of the particles of that system. Total number of possible arrangements of these particles is designated rho. So rho means number of microstates. In terms of arrangement of particles, there are two types of particles. One is distinguishable particles. Distinguishable particles are particles that are different from one another. For instance, A, B, and C. A is different from B, B is different from C. Number two types of particles is indistinguishable particles. These particles cannot be distinguished. They are all identical. Example, A, and A. These are indistinguishable particles. Now, for distinguishable particles, how do we get number of microstates or specific arrangement of the particles? Experiment shows that number of microstates for distinguishable particle is equal to n factorial, where n means number of particles. For example, for ABC system, this is a system and there are three distinguishable particles, A, B, and C. How do we now get the number of possible arrangements? Because there are three particles there, n is equal to 3, meaning that rho is equal to 3 factorial, and 3 factorial is 3 times 2 times 1, which means there are 6 microstates for system ABC, such as you can arrange it as A, B, C, A first, followed by B, and followed by C. You can decide to arrange it as A, followed by C, followed by B. You can arrange like B, followed by A, followed by C. Then you can arrange like B, followed by C, and followed by A. You can also arrange it as C, A, B. You can also arrange it as C, B, A. If you count the number of possible arrangements, it is 6 in number, which is in line with the equation rho equals 3 factorial. For indistinguishable particles, when you arrange A, and put the other A at the first, you won't be able to distinguish. You will still get one microstate. That is why the formula is different. The formula of microstates of indistinguishable particles is rho equals m factorial divided by n factorial bracket m minus n factorial, where m means number of available states or available positions, right? State is the same thing as position. So number of available positions is m, where n remains number of particles. Now, for instance, let us use the indistinguishable particles of system AAA. So for system AAA, n is equal to 3. N, which is the number of particles, is equal to 3. A, and A, 3 particles, where m is equal to 3 because there are 3 positions for the 3 particles. Position number 1, number 2, and number 3. So having known this, we can now use the formula for microstates of indistinguishable particles and substitute these values, where rho is equal to 3 factorial over 3 factorial divided by 3 minus 3 factorial, which will give us 3 factorial divided by 3 factorial 0 factorial. And 0 factorial is 1. So we have 3 factorial divided by 3 factorial. And 1 factorial is still 1. So 3 factorial times 1 is 3 factorial. So 3 factorial divided by 3 factorial will be 1. So we have 1 microstate despite the 3 particles present in system AAA. This now implies that system ABC has higher possible entropy, while system AAA has lower possible entropy, because the microstates for system ABC is 6, while the microstate of system AAA is only 1, meaning that there is only one possible way of arranging system AAA. Now, having understood the meaning of microstates, let's now move into the mathematical statement of third law of thermodynamics. The third law of thermodynamics states that the entropy of a system is proportional to the natural logarithm of number of microstates. Mathematically, S equals K ln rho, where S is the entropy, K is the Boltzmann's constant, which is 1.38 times 10 raised to the power minus 23 joule per Kelvin. And of course, rho is the number of microstates. Now, let us apply this law for system AAA, a system that has indistinguishable particles. For system AAA, of course, you know that the number of microstates is 1 only. Therefore, we substitute this 1 into the equation S equals K ln 1. You know that ln 1 is 0, so it will make everything to be 0. So for AAA, the entropy is 0. This now brings us to the third law statement, which states that as the temperature of a system approaches absolute 0, entropy becomes 0 for a perfect crystal. In this case, we take AAA as a perfect crystal because it has indistinguishable particles. And you can see that its entropy is 0 when the microstate is 1.